Okay, so good evening all. Can I proceed? Is there anyone in this chart window? Yeah, okay. Yeah, thank you. Okay, so good evening. So first of all, I would like to appreciate the brains behind this alumni talks. Okay, so I'm Ugadi Sunil. Currently, I'm doing PhD in IIT Madras. So today I will be presenting on concept of theories of failure. Okay, so these are the topics we are going to see for next 1 hour. So first, before jumping into failure of theories, so we need some basic understanding about how to represent the stress. So what are the various types of stresses you are having? What is the concept of principal planes, principal stress? What is hydrostatic stress, deviatoric stress? These details we require to understand theories of failure. So after getting into these basic fundamental topics, next we'll proceed further into the actual concepts of failure theories. So first let's get started with the what is the fundamental classification of stress. Of course, there are other types of stresses also, but for this constraint, we'll restrict ourselves to the normal stress as well as shear stresses. So these are the two fundamental types of stresses we are having. So of course, other than these two, we are having bending stresses or torsional stresses. But for this talk, so just understanding of normal and shear stress, that will be sufficient. So how you can classify this? So based on what parameter you are classifying stress as normal as well as shear. So here the parameter is how the applied stress is acting on the material. If you look at the normal stress, so what is the orientation of the stress here? So what is the difference you observe in this picture and in this picture? So this red arrow indicates direction of the applied stress. Okay, so in these two figures, so whatever the stress you are applying, that is acting perpendicular to the surface. So when it comes to this picture, the applied stress is parallel to the surface. Okay, so if your applied stress is perpendicular, that we call it as a normal stress. If it is parallel to the surface, that we call it as a shear stress. Okay, so the notation generally we use sigma to represent normal stresses and tau we use to represent the shear stresses. Okay, so again in normal stress we are having tensile mode and compressive mode. Okay, so this terminology itself it indicates compressive stress will be, it will be obviously compressing the material. When it comes to the tensile, it will be more or like a pulling action. Okay, so this is the fundamental classification of stress depending upon the how it is acting upon the body. Okay, so whether it is perpendicular or parallel. Okay, so this will be represented by sigma and this will be represented by tau. Okay, so next thing is how to represent the stress. So for example, this is your object. So at some point a stress is acting. How you will represent this? Okay, so generally whenever you see some stress acting on body, so generally what we do for our convenient, for easy, we'll resolve the stresses, right? So you might have done in basic engineering mechanics, right? So generally we resolve the stresses whenever it is acting on somebody. So generally, if you take three-dimensional body, you get one normal stress and two shear stresses. Okay, so you don't need to worry about this. You will understand as we move further. At this point of time, so just understand whenever there is some stress on the body, we'll resolve it. Okay, so you need to define the stress. What is the meaning of this? Defining the stress state. What does it indicate? Okay, so let's take one easy illustration. You are having one almara. Okay, you are having one almara. Obviously, this will be divided into rows and columns, right? So here I have placed one object. Okay, so if you want to convey, so where is the location of this object? How you will convey to other person? So obviously, what is the one way? You can indicate what is the row and what is the column where it is located, right? So you can give some row and column, something, right? So that the other person easily can understand where is the location of the object. Similarly, in order to understand the stress situation of the body, you need to give some notation. Okay, so that we call it as a defining stress state. Is this clear? For example, this is your object. On this, I am applying P, Q, R, S. Okay, P and Q will be equal magnitude, R and S will be in equal magnitude. Okay, so now how you will represent this stress? So what do you mean by defining the stress state? Okay, so just to make others understand how you will represent this PQRS. So that is what the meaning of definition of stress state. Okay, so first we will resolve this P and Q. So how many components you will get? So I'll get two components, one normal stress and one shear stress. Similarly, you can resolve R, Q and S also. Here also you will get corresponding stress components. The next question comes how to represent. You need to give the naming for this. Okay, so you need to give naming. How you will give? So first of all, look at this. Okay, I want to name this stress component. So what kind of stress it is? So obviously it is a normal stress. So you need to represent with sigma. Normal stress will be represented by sigma. So next thing is on which plane it is acting. This is the plane, right? On this plane, the stress is acting. Okay. To whom it is perpendicular. For example, if I define my axis as like this is X and this is Y. So whatever the plane you are talking about, to whom it is perpendicular, whether it is perpendicular to Y or perpendicular to X. If you represent the axes as here, X and Y, to whom it is perpendicular? It is perpendicular to the Y. So you need to put Y here. Okay. The next component will be what is the direction of stress, whether it is acting in Y direction or X direction. Obviously, it is acting in Y direction. So this will be sigma YY. Okay, so this is the name for this stress component. Sigma YY is the naming for this stress component. Similarly, what about this? So what kind of stress it is? Whether it is perpendicular or parallel to the surface. Again, it is normal stress. So obviously, it will be represented by sigma. The first component, the first subscript, it will talk about plane. Okay. So whether it is X plane or Y plane, to whom it is perpendicular. It is perpendicular to X, right? So it will be represented by X. So in what direction it is acting? What is the direction of stress? Again, it is acting in X direction. So it will be sigma XX. So similarly, here it is a shear stress acting on which plane? Whether it is X plane or Y plane. It is perpendicular to Y, right? Y plane. And what is the direction of stress? X, right? Tau YX. So like this, you can give the naming for this stress component. Okay. So you have taken an object on which some stress is acting. So initially you have resolved it and you have to name it. Okay. So we'll see what is the further. So this is the naming convention for whatever the stresses you resolve. Okay. So this is sigma x, tau xy. The first component, first subscript will talk about plane, and second subscript will talk about direction of the stress. Okay. So now this will be represented in terms of matrix. Okay. In diagonal, so this will be x and this will be y. So in diagonal, you need to put normal stresses. Okay. In rest of the position, so shear components will come. Okay. So it is sigma x, tau xy, okay, and tau yx and sigma y. That's it, right? Do you have any other component? Sigma x is there, sigma y is there, tau xy and tau yx. That's it. Okay. So 4 components you will get. So that will be represented in 2 by 2 matrix. Okay. So this is the meaning of a defining stress state at particular point. If you want to convey what is the stress situation at particular point, okay, so what you need to tell, you need to give this matrix. Okay. So similar to this, if you place one object in almara, so what details you are giving for others to understand what is the location of object? So you are giving at what row it is locating, right? First row, second row, and second row, and second column, right? So when you give 2 comma 2, the other person will can imagine where is the location of the object. So similarly, when some stress acting on some particular body, if you want to others to understand what is the stress situation at particular point, what details you have to give? So you have to give these details. So what is the stress in x direction, normal stress, and what is the normal stress in y direction at this point, and similarly shear components. Okay. So this is the meaning of defining stress state. Okay. So whenever some stress acting on particular point, so these are the details you need to establish to understand the stress situation at that particular point. Okay. So similarly, when you talk about 3-dimensional case, so what is the only difference you get? So here you got 2 by 2 matrix. So here you will get 3 by 3 matrix. So again, the notation, everything will be same. Okay. So in diagonal, you need to put normal stresses. Okay. At other positions, the shear components will come. Okay. So here maybe you will get, in earlier case, you got one normal and one shear on particular plane. So when it comes to the 3-dimension case, you got one normal, 2 shear components. Okay, so that is what we have seen. In general, a plane can have one normal stress and 2 shear stresses. Okay, is this clear? So what is the meaning of defining stress state? So that is what we have seen till now. So if you are having any queries, you can ask. Otherwise, we will move on further. Okay. So here I can't see your comments also. So if you are having any queries, you can post. So otherwise, we will proceed further. Okay. I hope it is clear. So just we have discussed what is the classification of stress. Okay, so depending upon the orientation, normal and shear, normal will be represented by sigma and shear will be represented by tau. Okay, so next we have seen how you will explain stress situation at particular point to somebody. Okay, so what are the details you need to give? So this stress matrix you need to give to understand the stress situation at particular point. Okay, so this is what we have seen. So next we'll move on further. So we'll define what is the principal stress. Okay, concept of principal stresses. Okay, so this is the object and these are the applied stresses. So when you resolve these stress components, you will see this kind of situation, right? Just I am resolving this, that's it. Okay. So what does it mean? The sigma y is normal stress on this particular plane, right? So because of this P, so whatever you are applying, so this much amount of normal stress you are getting. So what about this plane? For example, if I take some inclined plane within this object, so obviously because of PQRS, on this plane also you will get some normal stress and some shear stress, right? Or will it be equals to this sigma y? So for example, if you consider this plane, because of applied PQRS, here also I'll get some normal stress and some shear, right? Here I'm taking some other plane. Here also I'll get some normal and some shear. Right? Will it be equal? Since you are applying same PQRS on all the planes, do you get same amount of normal and shear? Obviously no. On different planes, you will get different amount of normal and shear stresses because of applied PQRS. Okay. So whatever stress you are applying, that will be resolving with different magnitudes on different planes. So what is the only variable here? Because of that, these stress values are changing. What is the variable? So here, the normal stress and shear stress. So whatever, how you are getting these two? Because of this applied stress. Okay. So whatever you are getting the sigma and tau, these are changing with respect to theta, right? So depending upon angle of plane, you are getting different values of sigma and tau. So obviously you are having some mathematical equations to calculate sigma and tau as a function of theta, but we are not moving into the equation. Just you need to understand the concept. That will be sufficient. Okay. So the point I am trying to make is, for the same applied PQRS, depending upon the angle of plane, you will get different values of normal and shear stress on that particular plane. Okay. So if you plot that in particular figure, so your x-axis is theta, angle of plane, and your y-axis is stresses, sigma and tau. Okay. As the theta changes, this is the trend of normal stress in your object. Okay. So what is the interesting features here? So what is something interesting here? So this is how shear stress is changing with respect to theta. If you look closely, the normal stress and shear stress both are reaching maximum and minimum values, and in that range these values are changing. Okay. So what is each theta here? Physically what it implies? Each theta will implies one particular plane in your object. Okay. It has some physical meaning. Okay. Each theta will represent one particular plane in your object. So what about these values? So this will represent one plane and the corresponding shear stress and corresponding normal stress on that particular plane, right? So now what is interesting here? Whenever sigma reaches to the maximum or minimum, so what is the corresponding shear stress on that particular plane? So this angle represents one particular plane, right? If you look at what is the corresponding normal stress and shear stress, normal stress is becoming maximum. At the same time, shear is becoming zero. So here also, normal stress is reaching some minimum and the corresponding shear is zero. The interesting features are, okay, so whenever you apply some stress within the object, there are certain planes, okay, on that particular planes, the normal stress is reaching maximum or minimum. At the same time, shear is becoming zero. Okay. That particular plane, we call it as a principal plane. So what is the definition of principal plane? the plane on which you are having either maximum or minimum normal stresses with zero shear. Okay, so these kind of planes we call it as a principal planes. So what is the principal stress? Obviously the corresponding maximum and minimum normal stresses we call it as a principal stresses. Clear? Is this fine? So just this is your object and you are applying stress. This PQRS we are splitting into different magnitudes of normal and shear components within this object. Okay, within this object you are having certain planes on which only normal stress is there and shear is becoming zero. Okay, so these kind of planes we are calling it as a principal planes, and this particular stress we are calling it as a principal stress. I hope it is clear. How to calculate the principal stresses? Obviously you should able to calculate the what is the magnitude of principal stress. So obviously whenever this is your object, some stress is applied on this object. Obviously how you will define it? You will define this stress situation on this particular object in terms of matrix, right? In terms of matrix you will represent. So now if I ask for what is the magnitudes of principal stresses in this object because of this applied stress, obviously you should able to calculate, right? Of course there are other ways like more circle is there, graphical methods are there. Okay, so obviously if you know the stress matrix, if you just calculate the eigenvalues of this particular stress matrix, the result will give the principal stresses. Obviously if it is 3 by 3 matrix, you will get 3 eigenvalues. Those 3 values are the principal stresses. If you are having 2 by 2 stress state, you will get 2 eigenvalues. Those are the 2 principal stresses. Okay, what about maximum shear? So this is the shear stress is changing in particular plane. Okay, so what will be the magnitude of this? Because of applied PQRS, so what is the maximum amount of shear you can get inside your object? So that also can be calculated once you know the principal stresses. Okay, so sigma max minus sigma min by 2. So this will give the what is the maximum possible shear stress you can have inside your object because of applied stress. Okay, yes, is this clear? So just whenever you apply stress on particular object on different planes, you will get different values of normal and shear. You are having certain specific planes on which your shear stress is zero and you are having only normal stresses. Those we call it as a principal stresses. Once you know the principal stresses, okay, you can calculate the shear stresses, the maximum shear also. Okay, so this is what we have seen till now. I hope it is clear. Okay, so we'll move on to concept of stress tensor. So this is your object. Okay, on this object I am applying some stress. The stress is defined in this way, 3 by 3 matrix. So obviously what will happen? It will deform because of this applied stress. So what do you mean by deformation? Either this volume will get expand or contract, or shape will change, right? Deformation is nothing but either volume get changes or shape changes, or sometimes you will see both, volume change plus shape change. Okay, so whatever the stress you are applying, this stress having 2 components. Okay, so one is hydrostatic component, other is deviatoric component. This hydrostatic component will be responsible for volume change in your material, and deviatoric component will be responsible for shape change of your material. Okay, so for a given stress tensor, you should able to separate what component is hydrostatic component and what component is deviatoric component. Okay, so how you will separate? Are you getting my point? So whenever you are applying stress, it is deforming the object. The deformation will be in terms of volume change and shape change. Some amount of stress will be helping for volume change and some amount of stress will be helping for shape change. Okay. So this component we call it as hydrostatic and deviatric. So once you know the stress tensor, how you will split this into two? Hydrostatic stress tensor, simply shear component should be 0. Okay. And what about diagonal? So diagonal should be replaced with the sigma m. So what is sigma m? Average of normal stresses, sigma x plus sigma y plus sigma z by 3. Okay. So you need to take average of this. So that will be sigma m. You need to place that. So this is the stress tensor which is causing for volume change in your material because of this applied stress tensor. So what about deviatric component? So just you need to subtract this. Okay. Place all shear components. Okay. In diagonal, so just you need to subtract average stress. Sigma x minus sigma m, sigma y minus sigma m, sigma z minus sigma m. Clear? So when you add these two, definitely you should able to get original stress tensor. Right? So just you add these two, again you will get original stress tensor whatever you are applying. Okay, so this is about hydrostatic and deviatric stress tensor in your object. Is this clear? So whenever you are applying stress, there will be two components. One is hydrostatic and other is a deviatric component. Hydrostatic will be helping for volume change in your material. A deviatric will be helping for shape change in your material. Okay. The other concept is stress invariance. These are simply mathematical operations. You might have done in matrix chapter, mathematics. So how to calculate the first invariant of matrix, second invariant, third invariant. Okay, so the same concepts will be applied for stress matrix also. How you calculate first invariant? So just you add the some diagonal elements. So that will be the first invariant of the stress matrix. So what about second invariant? For second invariant, you need to add the minor of each diagonal element. Okay. So minor of sigma x plus minor of sigma y plus minor of sigma z. How you calculate minor? For example, if I want minor of sigma x, I need to delete this row and column and calculate the determinant for remaining part, AD minus BC. That will be the minor of sigma x. If I want minor of sigma y, just eliminate this row and column. For rest of the things, I need to calculate the det. So that's how you can calculate second invariant of the stress matrix. So what about third invariant? So simply calculate the determinant. So that will give the third invariant. Okay. Yeah. So these are the basic fundamentals you require to understand the theories of failure. Okay. So basically you should know what do you mean by principal stress. So what is the deviatric stress tensor, and similarly what are the first invariant, second invariant and third invariants. Okay. Any questions till now? Give me a second. If you're having any questions, you can raise. Otherwise, we'll move on further. Okay. So now we'll jump into theories of failure. So first of all, you need to define what is failure. So this is not a term which is having absolute meaning, right? So it is depends upon the perspective. For someone, earning money might be success, right? So for someone, following passion might be success. So like this, failure is not having some particular definition. So that depends upon the perspective. So you need to define it. In this context, what is failure for engineering perspective? In engineering perspective, So in general, what is the when you consider it is a fail and it is success, you put some expectations, right? If you don't meet that expectation, obviously you consider it as a fail, and if you meet expectations, you consider it as a fail, a success, right? So failure in the sense it is not up to the expectations. For engineering design, what do you expect? Okay, so in case of engineering applications, we don't want even plastic deformation. Forget about fracture. Even we don't want shape change in your structure, right? So for example, I bought a chair, a metal chair. So when I sit, if it get deforms, whether it is a successful design or failure design, it is not get fractured, but still it is a considered as a failure. So because there is a yielding in your material. Okay, for most of the engineering applications, even yielding is not allowed. So just I want to define what is a failure in this context. Okay, so even plastic deformation is considered as a failure for engineering applications. Okay, so now why you required theories of failure? So this is the core idea of theories of failure. Okay, so we'll spend more time here. So once you understand this, then everything else will be easy. Okay, so for example, you are running a material testing laboratory service. Okay, you are running a laboratory. Okay, so where you are providing mechanical testing services. Okay, so for example, let's take in other hand some application. Okay, so one customer has come to you. Okay, he is using some material. In this material, he is going to use under normal stress situations. He is using some for some application. In that application, the stress is something acting like this. Okay, he wants to know up to what stress I can go without yielding this material. So obviously he has to perform some material testing, right? He has come to you. So what test you will do? So this is his application. He's having an object. Okay, some normal stress is acting. You want to know up to what stress he can use safely this material without getting deformation. So obviously, what test you will do? Simply you can perform tensile test, right? So what you get when you perform tensile test? So what you do in tensile test? Simply you take some specimen, you prepare as per the standard, and you apply progressive loading, right? So you will get a beautiful curve, right? Of course. Okay, somewhere you will indicate yield point. Let's say you got yield point as some 400 MPa. So what you will suggest to your customer? So you can use this material without yielding up to 400 MPa. So that's what you suggest. Of course, if you want, you can add some factor of safety. Okay, so where is the theories of failure here? You are able to determine. So what is a failure point? Then where is the concept of this theories of failure? Simply you have performed a tensile test and you are able to tell. So what is the failure point? Right? So let's take other case. The second customer has come where in his application, okay, the stress is something like this. In this direction, normal stress is there, and in this direction also stress is there in that particular application. Okay, he wants to know what is the limiting value, up to what stress he can use this material safely without plastic deformation. Okay, he has come to you, to your lab, and asked for what is the safe limit. Okay, so what you will suggest? So what you will do? Again, will you do same uniaxial tensile test? Obviously, in your laboratory, you will be having only uniaxial tensile test. Do you have any biaxial testing equipment in your laboratory? Do you have this kind of equipment where you can apply the load in 2 axes? No, right? You are having only uniaxial. Again, will you do same uniaxial and it will give the same yield point to this fellow also? Will it be accurate? Again, you do same uniaxial tensile test and you get some yield point. And will it work here? Obviously, it won't work, right? So, what is the reason? In your laboratory, your testing condition is different. The customer application is different. Obviously, you cannot give same result. Otherwise, will you prepare some equipment where you can apply biaxial? Is that possible? So other customer will bring other kind of stress state. So this can be stress state in his application. Will you design one more equipment? The point I'm trying to make is in practical application, you can have n number of stress combinations. When it comes to the laboratory, we are having a limitation. Obviously, we cannot create equipments which can satisfy this n number of stress states. You are having only one equipment which can apply the stress in uniaxial. That's it. Or either you can compress. Right? Then how you will determine failure point? Obviously, without knowing the safe limit, you cannot design some structure. So that is not preferable, right? Whenever you use some material in certain application, you need to know what is the limiting value. Right? So what you will do now? So that's where theories of failure has come. So what this theories of failure does? This theories of failure will take the data of simple uniaxial tensile test. Okay, you perform the test on uniaxial only, but you apply these theories of failure and predict the failure point in complex stress state. So what are the complex stress state here? Either it can be biaxial, okay, or either it can be triaxial. You can have n number of combinations of stresses in practical applications. You can determine failure in practical applications, okay, so just by conducting uniaxial tensile test if you use theories of failure. Okay, so that is the whole idea of theories of failure. Okay, so directly you cannot use uniaxial tensile test result for complex stress state. You need to process by using the concepts of theories of failure. Is this fine? It's clear. We'll move further. Okay, so now we'll introduce what are the different theories of failure we are having. The first one is maximum principal stress theory. So this also call it as a Rankine's theory. Okay, so what this says, failure will occur when the maximum principal stress in application reaches the value corresponding to uniaxial loading. Okay, so here we are having two things. So one is stress situation in your laboratory and stress situation in your application. Okay. So what parameter you are going to use here for determining whether it is safe or unsafe? You are going to use maximum principal stress. So you already know what is the principal stress, right? What is the definition of principal stress? How to find out the maximum and minimum principal stresses if you know the stress matrix, right? So these things just now have seen. By using this principal stress, you can determine whether it is safe or unsafe. How will you determine? Okay. So just we divide into two halves screen. Okay. So in one side you are having your laboratory situation. In other hand you are having your actual application. Okay. So what is the parameter here to determine whether it is failure or successful design? Maximum principal stress. So this is the parameter we are going to judge based on which maximum principal stress. Okay, in your application, whatever might be the your stress situation, either you can have triaxial, biaxial, or some shear. So whatever can be the stress, can you find out what is the maximum principal stress in your application? Can you find out, right? Obviously, what will be there? Obviously, it will be at the end of the day, it will be just 3 by 3 matrix, right? So whatever stress combination you are having in your application, it can't be beyond this, right? So now, once you know this, how you will find out maximum principal stress? So just now I have seen, at least you should know there is a way to calculate the maximum principal stress, right? You can calculate eigenvalues, or you can use the concepts of Mohr circle. There are direct formulas also. Okay, so once I know the stress situation, definitely I can find out what is the principal stress, maximum principal stress. You find out that, okay, sigma max in your application. Okay, so otherwise, the next thing is in laboratory what you are doing. So obviously you are having only one way, uniaxial tensile test, right? So when it will fail, at failure point, failure in the sense yield point, right? At this point, what is the stress situation, stress matrix at failure point? Is there any shear components here? I am not applying any shear, right? So all the values will be 0. And in y direction, at failure point, the stress will be reached to yield point, right? Yield stress, sigma yield. And other components will be 0, 0, 0, right? So this is the stress situation at failure point. Okay. So now, what can be the maximum principal stress at failure point? Can you find out this? What is the maximum principal stress? Obviously, now itself it is under principal stress condition because there is no shear, right? What is the maximum principal stress here? Sigma yield. Yield point itself, it is the maximum principal stress. So now how you give this result? How you frame the result, final conclusion? So what you suggest to your customer? So this material can bear up to a stress where your maximum principal stress won't cross this limit. So let's say your maximum principal stress you got some around 400 MPa. So what you suggest? So whatever stress you want, you can apply. So whether biaxial, triaxial, or different combination of shear, whatever you want, you can apply. So, but what is the only thing you need to be assured? Ensure that in your application, your maximum principal stress won't cross this. So that is the only thing you need to remember. Okay. So here, what is the parameter? The maximum principal stress is the parameter which decides whether it is successful design or failure design. Okay. After performing your uniaxial tensile test, what is the sentence you will frame? For example, if it is yield point 400 MPa, so this material can be used in a state where the maximum principal stress will not exceed this value. So that's how you will give the result. Is this fine? Okay, so that's what we have seen here. Failure will occur when the maximum principal stress in your application, it reaches the value corresponding to uniaxial loading. Okay, so that is the only thing you need to be assured. So just make sure So whatever stress situation in your application, just don't exceed the maximum principal stress of uniaxial tensile test. So that is what this theory says. Okay. So what is this safe region? For example, sigma 1, sigma 2 and sigma 3. These are the principal stresses in your application. Okay. So now if sigma 1 is bigger value, obviously who will decide the failure? You no need to look at these two fellows. Just look at sigma 1. Okay. If sigma 1 is less than the yield point, obviously you will be safe. Right. If sigma 2 is larger, you need to look at this guy. Make sure in your application sigma 2 won't exceed this yield point. Until and unless you are less than this, you will be safe. Okay. So this will be the safe region for a maximum principal stress theory. Okay. So what are these points? Boundary points. So these are the yield points. So yield is nothing but maximum principal stress, right? So this is about maximum principal stress. Is this clear? The next thing is maximum shear stress theory. Again, it is also same. What is the only difference you observe here? The parameter is changing. That's it. Earlier you have used maximum principal stress. Now you are using maximum shear stress to judge whether it is a successful design or a failure design. Okay. So again, it is same. Okay. So you just take the specimen to your laboratory. Okay. You perform uniaxial tensile test. Okay. So what will be the stress matrix at the failure point? So everything will be 0 except sigma y. This is yield, not sigma y. Right. This is the stress situation at failure point. Right. So this is the failure point. So now what you need to calculate? You don't give the result like this, right? This is the maximum stress. This is the yield point. That's how it won't work. So what is the final conclusion you will frame? If you are following maximum shear stress or Tresca theory, you need to find out at the failure point what is the maximum shear. How will you find out? So I have seen one slide how to find out the maximum shear. So just you need to know what is the maximum principal stress minus what is the minimum principal stress, right? Divided by 2. So this will give the maximum shear at the failure point. So what value you will get? Sigma yield by 2. Right? So this is the maximum shear your material can sustain before it get failed. Okay, so what is the final conclusion you will give to your customer? So whatever the stress situation it can be, just make sure your maximum shear stress won't exceed this. Okay, so how this guy will calculate what is the maximum shear? Again, here also you'll be having his own stress matrix. From this, first you will calculate what is the maximum principal stresses and what is the minimum principal stress. So once he knows these two values, he can calculate what is the maximum shear he can have, and he will compare with the result what you have give. That's it. Is this clear? Okay, only parameter will get changed. So this is the maximum shear stress theory. Okay, so again these are some equations to find out what is the safe region. The only thing is just you need to calculate the maximum shear. That's it. Okay. So next thing is von Mises theory or distortion energy theory. Okay. So here we'll take some time. So what is the von Mises theory? What parameter he is using? He is using second invariant of Debye-Autrix stress tensor. So this is the parameter he is using to tell whether it is a successful design or a failure design. So you already introduced what is the deviatrix stress tensor, right? If you know the stress matrix, how you will find out deviatric portion? So just from the diagonal elements, you need to subtract average value. If you does that, you will get deviatric stress tensor. So how about second invariant? So that is minor of each diagonal element. Summation we have to do. Minor of sigma x plus minor of sigma y plus minor of sigma z. So that is the parameter is going to use to for a designing purpose. Okay. So just we will see. So what equations we will get when you compare this second invariant of deviatrix stress tensor. Okay. So just I will show some equations. I hope it is clear, right? So this is the deviatrix stress tensor, right? So earlier it will be like only sigma x, sigma y, sigma z. But if you want to get the only deviatric portion, so what you need to do? From the diagonal elements, okay, you need to subtract average value, right? From the diagonal elements, you need to subtract the, average value. Okay. How you will calculate second invariant? So just minor of this plus minor of this plus minor of this element. So if you does that, you will get this expression 1 by 6 sigma x minus sigma y whole square plus sigma y minus sigma z whole square sigma z minus sigma x whole square plus 6 into tau xy square yz square plus xz square. Okay. So this is the second invariant of stress deviator matrix. Okay. So you keep this in one hand. So what is the other thing? Other side you are having your laboratory situation, right? Where you are performing uniaxial tensile test, where you are having only y component. For this also you need to calculate what is the second invariant of stress deviator. Okay, so if you calculate that, so just you need to substitute this. Already you are having expression, right? For second invariant of a deviatrix stress tensor. Just you substitute that values, you will get 2 by 6 sigma yield square. So this is the second invariant of deviatrix stress tensor. So now what you need to do? Just compare, right? So that is what we are doing. Application one hand and laboratory result one hand. So this is the second invariant of stress deviatric matrix in your application, and this is the at failure point in your laboratory. If you compare these two, what you got? You will get this expression. You no need to worry about the equation, just understand the concept. Okay. This is the yield you got from uniaxial, and right hand side you are having one big equation. Okay. So what is the conclusion you will made here? So let's assume this right hand side parameter completely as a parameter A. Okay. So what is the conclusions you will draw? If that right hand side it is completely A, so make sure this parameter in your application is not exceeding the yield point of tensile test. Okay. In that case you will be safe. If this parameter exceeds the yield point, okay, your material going to fail. So that is what the von Mises said. Okay, so if you look at the definition, yielding will occur when the second invariant of the stress deviator in your application exceeds the second invariant of the stress deviator in uniaxial tensile test. So that is what the definition he has given. So but the problem is he could not explain what is the physical meaning of this. So just he has given some mathematical equations, that's it. He could not explain physically what it implies. Okay, so later on people able to find out. So that is nothing but when you assume distortion energy as a parameter, you are getting same result. So that's how people have later on come to this conclusion, distortion energy criterion. Initially it was purely mathematical. Okay, one mysis could not explain what is the physical meaning of this. Okay, so that is about one mysis. So when you consider this distortion energy, you will get this elliptical safe region. Okay, so we are not going into this. Okay, so this is about three theories of failure. Okay, so when you compare these three theories, okay, so when you merge these three curves, you will get this kind of region. Okay, so now from this graph, so which one do you think it is more safe? Obviously Tresca criteria, right? So if you follow this criteria for designing purpose, so you will be safe according to Rankines as well as von Mises as well as Tresca. Right? This is the most conservative theory, Tresca theory, or maximum shear stress theory. Okay, so of course we do have other theories of failure, but we cannot cover all the theories in single go. Okay, so just I am touching upon what are the fundamentals you require to understand the theories of failure, and three most used failure theories for designing purpose. Okay, so this is about today's session. Okay, so if you are having any queries, you can ask. Okay, so otherwise we'll conclude. Okay, so thank you all. Any queries? Okay then. Okay, see you.